So let us proceed for 27th class. Application of Fourier equation. Application of Fourier equation. So in the previous class we have discussed the heat conduction equation in three-dimensional Cartesian coordinate system. We have derived that equation and we have gone through the statement of the Fourier heat conduction equation in three dimensions with respect to the spherical polar coordinate system as well as the cylindrical polar coordinate system. Now, in today's class, we will discuss some application of the Fourier equation. Basically, those systems will be, even though they are the three-dimensional system, but posing some conditions therein, we will restrict them to one dimension and try to evaluate some results which are of immense practical importance so far as the design of the furnaces are concerned. So let us consider the case number 1. Case number 1, heat flow through a plane wall. Heat flow through a plane wall with no heat generation. That means in a straightforward manner we are assuming that there is no chemical reaction or any physical process leading to the heat absorption or heat evolution is there. So let us consider a plane wall. I am mentioning the plane wall because of the fact that the only x direction that I am going to consider here. By putting the assumption that the dimensions of the same plane wall along the y and z axis are such that the heat flow along those directions may be neglected. This is the condition by the virtue of which a three-dimensional system may be reduced to a one-dimensional system. So in the case of plane wall, we are considering the x dimension only. Let us suppose this wall has a temperature T1 and this wall has a temperature T2, and from T1 to T2 the heat flow is there. Let us suppose the coordinate of this straight line is x equal to 0 and the coordinate of this straight line, this is another face of this plane wall, is the coordinate has the x equal to L. So definitely the width of this plane wall is L, right? Because of the fact that the heat flow always downhill a temperature scale according to the second law of thermodynamics, so let us suppose this is our temperature profile. A linear temperature profile has been assumed. So let K and alpha, let K and alpha as thermal conductivity and thermal diffusivity of the material of the plane wall, of the material of the plane wall respectively. Assuming the fact that heat transfer is taking place, in x direction only, and K, that is the thermal conductivity, doesn't vary with respect to temperature. The Fourier equation may be given as, Fourier equation can be given as, the Fourier equation can be given as, if a steady state heat flow is there, so you can write here in the formulation itself, steady state heat flow through a plane wall with no heat generation. So the Fourier equation can be given as, this was the Fourier equation. Since there is no heat generation, so this quantity will be 0. Okay. Steady state heat flow is there, so this quantity is also equal to 0. So we can write alpha del square T is equal to 0. That means del square T is equal to 0, or we can write d2T by dx2 plus d2T by dy2 plus d2T by dz2 is equal to 0. But since the heat flow is taking place in the one direction only, so these quantities will also get cancelled. So the final form of the equation is this: d2T by dx2 is equal to 0. Now we have to solve this differential equation with respect to the boundary condition which is prevailing in the present case, and we will try to arrive at the exact temperature profile for the present case. So let us proceed for that, starting from d2T by dx2 is equal to 0. So d2T by dx2 is equal to 0, or we can write d upon dx, dt upon dx, that should be equal to 0, or we can write d dt by dx is equal to 0. When you integrate this equation, then you will find dt upon dx is equal to C1. Let it be equation number 1. Starting from the equation number 1 itself now, so we can write dt is equal to C1 dx. When you integrate further, then the second equation that will be generated, that is the t is equal to C1x plus C2. Better to write this equation number 1. That is not essential. So t is equal to C1x plus C2 is the equation for the temperature profile in the case of a plane wall in which there is no heat generation as well as heat is flowing along the x-axis only. So the second task which is in front of ourselves is to evaluate the constant of integration C1 and C2. So the pertaining boundary conditions are number 1, x is equal to 0, t is equal to t1. So from equation number 1, we can write here t1 is equal to c1 into 0 plus c2. So the value of the second integration constant has been arrived as c2 is equal to t1. Now take the second boundary condition. For the present case, is the x is equal to L, so t is equal to t2, so we can write t2 is equal to c1L plus c2, that is equal to c1L plus c2 is equal to t1. So the value of c1 comes as t2 minus t1 divided by L. Let it be question number 3. This is our value of the first integration constant. So from the boundary conditions, we have evaluated all those required constants here. So the equation for the temperature profile putting the values for C1 and C2 in equation number 1, temperature profile for the present case, is T is equal to C1x plus C2, that is T is equal to T2 minus T1 divided by L into x plus C2, that is the T1. So this is the temperature profile for the present case. Now the second task is to evaluate, or it can be written as T, because T1 is greater than T2, so write accordingly T1 minus T2 divided by L into x. Instead, you should assume this equation number 4. What should be our next task? Next task to evaluate the heat flux. Next task is to evaluate the heat flux. That means the quantity of heat energy which is flowing from this to this side per unit area, per unit time, per unit area. So Q is equal to, that is heat flux that is equal to according to the Fourier law Ka dt upon dx, and where this dt by dx value gradient should be taken at x is equal to 0. So dt upon dx at x is equal to 0. Now evaluate this quantity dt upon ds from equation number 4. dt by dx at x is equal to 0, that should be equal to, this is a constant quantity, so 0, and this is equal to 1, differential coefficient of x is equal to 1 at x is equal to 0, so that will be equal to t2 minus t1 divided by L. So this is the expression for the temperature gradient. This is the expression for the temperature gradient. See, you can easily examine the temperature gradient here is negative. That is, heat must fall down a temperature scale. T2 is smaller than T1, so T2 minus T1 divided by L is a negative quantity. L cannot be a negative quantity, so that is the negative quantity. But the heat flux, that will be always a positive quantity, so that will be equal to minus Ka dt by dx, that is equal to Ka T1 minus T2 divided by L. This is always a positive quantity, K is a positive quantity, area is a positive quantity, T1 is greater than T2, so T1 minus T2 is a positive quantity, L is a positive quantity, so this will be greater than 0 all the way. This expression seems to be very simple in nature, but it generates a new idea regarding the concept of thermal resistance, and also it leads to the concept of equivalence in an electric circuit as well as in thermal circuit. So let it be question number 5, and we will start the discussion from the equation number 5 itself now. So the equation number 5 can be rearranged as that is the practical application of such type of things. That's why I am giving more emphasis on this. So revisiting the equation number 5, you can write here. So Q is equal to, it may be written as T1 minus T2 divided by L upon Ka. Okay. Another form of this equation number 5. Now let us try to establish an equivalence between a heat flow study as well as an electric flow study. Let us suppose I am assuming an electric circuit where there are 2 points A and B, 1 and 2, having the potential V1 and V2, where V1 is greater than V2, so definitely the current will start to flow from the point number 1 to 2. Let us suppose there is a resistance R there, then definitely the current that is flowing through this, that may be given as per the Ohm's law, that is V1 minus V2 divided by R. Okay. Now with respect to equation number 5, if I am assuming a thermal circuit in a manner that on the same guideline as appears in the case of an electric circuit, if I am assuming that there are the 2 points which is respectively at the temperature T1 and T2, where T1 is greater than T2, so definitely the heat will start to flow from the point number 1 to point number 2. It has to come across through a resistance that is called here the thermal resistance, and the flow quantity which is Q here, that can be written as Q is equal to T1 minus T2 divided by L upon Ka. Now try to compare this equation with this equation. Now the flow quantity in both the cases, that is Q and I, the temperature difference is the driving force here, whereas the potential difference is a driving force here for electrical circuits. It has to face some resistance. So in the case of the heat flow, it has to pass through a thermal resistance L upon K, that may be due to the refractory lining in the furnace, that may be due to the composite lining in the furnace, where more than one refractory linings are there in the case of many industrial furnaces. So if you compare these two equations, then you will arrive at the fact that the L by Ka is nothing but, this is called the thermal resistance, and that should be equal to L upon Ka. This is the case in the case of the conductive heat flow. On a similar sort, if I am considering a convective heat transfer, then in the case of convective heat transfer, in the previous classes, in the preliminary classes, I have give you the idea, that is the heat flux in that case, that will be equal to H into A into temperature of the surface minus temperature of the fluid. So this is your temperature difference. So it can be written as Ts minus Tf divided by 1 upon Ha. So for that case as well, this is also a thermal resistance, but this thermal resistance is convective, and so far as this thermal resistance is concerned, this is R theoretical, this is called conductive resistance. So whenever and wherever we have to design a furnace in such a manner that the heat energy which is being produced in the furnace, either through the induction heating or through the other means, that is the burning of fuels, if you are knowing the final temperature of the furnace, that is the temperature which must be there at the farthest side, then you can easily design that what should be the length of the refractory lining in that case. That knowing the thermal conductivity in area, you can easily arrive that what should be the thickness of the refractory lining in an industrial furnace. This is the practical application of such type of special cases of Fourier law. Here I have assumed the two types of thermal resistances, that is the conductive resistance as well as the convective resistance. So many times as furnace operates in the air, in the open air it operates. So the concept of convective resistance is of immense importance so far as the designing regarding the thickness of the different refractory linings are concerned. So in the cases of industrial furnaces, industrial furnaces, there may be composite refractory lining. The length of which, or the thickness of which, better to write here the thicknesses of which can be arrived through heat flow studies. Referring to the thermal circuit as below, thermal circuit as below. What I have assumed the thermal circuit here. Let us suppose the ambient air has a temperature Ta and the convective heat transfer coefficient is Ha. Okay. The heat energy passes, it strikes at this surface, the first lining, initial point of the first lining. It will arrive, let us say, at temperature T2. It will further proceed T3, T4, and finally goes to the air again, where the temperature of the air here is Tb and the convective heat transfer coefficient is Hb. So if an analogous electric circuit for the present case may be assumed, then you can write here that these are the 2 points at the temperature Ta and temperature Tb, and if these are the length of the refractory linings L1, L2, L3 with their respective thermal conductivity as K1, K2, K3, then the heat flow through this furnace will have to pass through this length L1, L2, L3, that is the 3 refractory linings. That means some sort of resistances will be offered by this L1 thickness of the refractory lining, L2 thickness of the refractory lining, L3 thickness of the refractory lining. So let us suppose at air it is arriving at this point, so it has to go through a convective resistance Ra. After that it will come across here R1, it will further come across at R2, it will further come across through R3, this, and again it has to pass through a convective resistance, that is the Rb. So through the equivalence with electrical circuit, the total resistance R total, that will be equal to R convective, R thermal convective plus R thermal conductive. That should be equal to Ra value. What should be equal to? This should be equal to 1 upon Ha into A. Same area it had to pass. I have assumed that the area, this, and this all are equal. So 1 by HA1, HAA plus L1 upon K1A plus L2 upon K2A plus L3 upon K3A plus 1 upon HBA. So this is the thermal resistance through which it has to pass. So if you are knowing the total thermal resistance that you are calculating with respect to this formula, all the quantities on the shop floor will be available to you. So you can easily calculate the R total, from where using the electrical analogy you can easily find out that what is the value of Q, that is the heat flux in the present case. If you have to arrive at a particular heat flow rate or heat flux in the case of any industrial furnaces, then you can easily adjust, you cannot adjust the HA and HB value, but the quantity which is in your control is the thickness of the refractory lining. That altering the value of L1, L2 and L3, a desired value of heat flux can be achieved in the case of any industrial furnaces. So, by utilizing such type of principle, you can easily design that what should be the thickness of the first refractory lining, what should be the thickness of the second refractory lining, and what should be the thickness of the third refractory lining. This is regarded as the most important industrial practical example of the heat flow study through the Fourier equation. This is all about the Cartesian coordinate system, extended Fourier equation in the Cartesian coordinate system. So let us take an example where the Fourier heat conduction in the cylindrical polar coordinate is to be used. Let us try one application from that thing also. So now let us assume, or let us go through the heat flow through a cylinder without any heat generation. Heat flow study through a cylindrical system. So the case number 2 is the heat flow through a cylinder with no heat generation. Now here, assuming the heat flow in the radial direction only, that is, we are not considering the heat flow along the theta direction as well as the z direction. Rather, we are assuming that the heat flow is taking place along the radial direction only in the case of a cylinder whose internal diameter is R1 and the external diameter is R2. So, the Fourier equation may be given as d by 2t by d by r2 plus 1 by r d by t by d by r, that should be equal to 0. Since the heat flow is taking place in the radial direction only, we are considering the r direction only, so this partial derivative can be accordingly changed into the normal derivative. So d2t by dr2 plus 1 by r dt by dr is equal to 0. The solution of this differential equation through utilization of the boundary conditions therein, you can arrive at the temperature profile in the cylindrical system. You may ask me the question that where this cylindrical system may be utilized. The cylindrical system can be utilized in practical purpose to determine the temperature profile in the case of blast furnace, which is cylindrical in shape, to design the cylindrical tube furnaces, which is generally used in the ceramics engineering and also in the metallurgical engineering so far the composite material preparation is concerned. So those things can be easily designed or easily arrived by utilizing such principles. So d2t by dr2 plus 1 by r dt by dr is equal to 0. Multiplying the whole expression by r d2t by dr2 plus dt by dr is equal to 0, or we can say d by dr r dt by dr, that should be equal to 0, or we can say dr dt by dr, that should be equal to 0. Integrate this, or r dt by dr, that is equal to c1, or dt is equal to c1 dr by r. Integrate this again, so t is equal to c1 ln r plus c2. This equation number 1 is the temperature profile for the cylindrical system. Now again, as in the previous case we have gone through, you have to take the boundary condition for the present case to evaluate C1 and C2. So the boundary conditions are at R equal to R1, let temperature equal to T1. So T1 is equal to C1 ln R1 plus C2, and R is equal to R2, let temperature is equal to T is equal to T2. So the T2 is equal to C1 ln R2 plus C2. When you solve this equation, please do it from yourself. You will arrive at the value C1 is equal to, C1 will be arrived as this minus this, T1 minus T2 divided by ln R1 by R2. Let it be question number 2. And the value of C2 will arrive as, please do it yourself, 2 ln R1 minus T1 ln R2 divided by ln R1 upon R2. Now from the equation number 1, 2 and 3, so from equation number 1, 2 and 3, from equations 1, 2 and 3, the expression for the temperature profile comes as T is equal to C1 ln R, that is the T1 minus T2 ln R divided by ln R2 upon R1, R1 upon R2 plus C2, that is the T2 ln R1 minus T1 ln R2 divided by ln R1 upon R2. When you will further solve it, the expression will come as the final form of equation that I am writing here. So that will be equal to T1 ln R2 upon R plus T2 ln R upon R1 divided by log E R1 upon R2. Since quantity, this T cannot be a negative quantity, you can easily emphasize here. If you take the plan view of this case, if you take the plan view of this present case, and a cylinder in the plan view of a cylinder, this is your R1 radius, the internal radius of the cylindrical system. This has the temperature T1. This is the external radius of the cylindrical system. This has the temperature T2. If the heat flow is taking place from the inner wall to the outer one, so T1 is greater than T2, and if I am assuming a hypothetical cylindrical surface at a radius r, which is a temperature T, so definitely R1 is less than R, that will be less than R2. So this quantity R2 by R is a positive quantity, R by R1 is a positive quantity, that is the quantity greater than 1. R1 by R2 if you transform this, this will come as R2 upon R1. R2 upon R1 is a quantity greater than 1. So this temperature will be a positive quantity. So equation 4 is the desired expression for temperature profile. Once the equation for the temperature profile is known, so you can easily evaluate the heat flux Q is equal to minus Ka into dt by dr, that is the temperature gradient around the radial direction if the heat flow is taking place from the inner cylindrical surface to the outer one. So definitely the temperature gradient needs to be taken at the point r is equal to r1. So minus Ka dt by dr at r is equal to r1. If you evaluate this quantity, that is equal to Ka dt by dr, that is equal to C1 by r at r is equal to r1, that is equal to minus Ka C1 upon r1. If you go through all the necessary steps, you will find that it will come as minus 2 pi KL into T2 minus T1 divided by log R1 by R2. So that can be written as T2 minus T1 divided by 1 upon 2 pi KL log R1 by R2, that is equal to T2 minus T1 divided by thermal resistance. So in the case of a cylindrical system, the thermal resistance for the cylinder, that should be equal to 1 by 2 pi KL ln R1 by R2. Here it needs to be emphasized here, the Q is again a positive quantity, still T2 is lesser than T1, so T2 minus T1 is a negative quantity, but 1 by 2 pi KL ln R1 by R2 is a lesser quantity, less than 1, so that logarithm will be negative in nature, so these two negative will create again a positive quantity, so the heat flux in this case is again a positive quantity. So this will complete completing your the cylindrical system as well. Please go through the numerical problem for all the cases that we have discussed today, and in the next class, from the next classes, we will see that how this Fourier equation can be applied for the cases in which, in all the systems, apart from the no heat generation case, the case will be discussed in which the heat generation is going on. Thank you.